Here's the trap. Your RAG system can have great embeddings and still lose because FAISS was trained badly.
Exactly. A lot of teams think retrieval quality is mostly the model, but once you choose certain FAISS indexes, the training step quietly decides how much recall you keep or throw away.
So, this is not model training. This is index training. And if you ignore it, your search gets fast and wrong.
Right. In FAISS, some indexes need training because they learn structure from your vectors before they can compress or partition them. If that structure is off, the nearest neighbors you wanted get routed to the wrong place or approximated badly.
Which indexes are we talking about? Because this is where people get vague fast.
The simple rule is flat indexes do not need training. Index flat L2 and index flat IP, no training. HNSW also does not have a train phase, but IVF indexes need training. PQ-based indexes need training, and combinations like IVF PQ or OPQ plus IVF definitely need training.
Give me the practical translation. I'm building a RAG system. When does this become my problem?
The moment you move beyond exact search to get lower latency or smaller memory. Say you switch from index flat IP to IVF PQ for a few million chunks. Now you must train centroids for IVF, codebooks for PQ, maybe a rotation for OPQ. That training data becomes part of your retrieval behavior.
So, if I train on junk, I don't just get a slightly worse index. I get a search system that confidently misses the right evidence.
Yes, and that is the dangerous part. Poor training usually hurts recall before anyone notices. The system still returns something, just not the best chunk. In RAG, that means the model answers from weaker context and sounds plausible while being less grounded.
Let's make that concrete.
Imagine a support chatbot for a SaaS product. Your real traffic is full of billing disputes, API auth errors, and plan limits. But you trained the FAISS IVF PQ index on a random sample that overrepresents onboarding docs and marketing pages. The partitions and compression are now tuned to the wrong geometry. Queries about billing land in coarser buckets with worse candidates, and recall drops exactly where users are angry and expensive.
That's a power shift. The index is deciding which business problems get solved well and which ones get quietly downgraded.
That's a good way to put it. Training data quality is not just about cleanliness. It is about representativeness. The vectors you train on should reflect the distribution you will search over and the kinds of queries that matter.
What counts as bad training data here? Duplicates? Stale content? Skew?
All three. If your sample is tiny, you get unstable centroids and weak codebooks. If it is skewed toward one document type, your partitions favor that region of vector space. If it includes outdated or malformed chunks, the learned structure wastes capacity modeling noise. And if you train before your chunking strategy stabilizes, you can bake in the wrong shape entirely.
So a team can accidentally optimize retrieval for the easy stuff and lose on the hard stuff that users actually remember.
Yes. And recall loss is often uneven. You may keep headline metrics looking decent while failing on narrow but critical intents, like legal clauses, refund rules, or internal runbooks. The winners are broad, frequent patterns. The losers are edge cases with real consequences.
How does poor training show up in practice? What does the failure feel like?
Usually like this. Top K results look vaguely related, but the exact supporting chunk is missing more often than expected. You increase K to compensate, latency rises, and generation quality still wobbles because the right evidence never made the candidate set. Then someone blames the LLM, even though retrieval lost upstream.
Give me another example, but one engineers will recognize immediately.
Suppose you index code-based docs and internal tickets. During a reindex, you train IVF on only docs because tickets were still loading. Later, developers ask about a production error code that mostly appears in tickets. The query gets assigned using centroids learned from polished documentation language, not messy incident language. Ticket-heavy neighborhoods are poorly represented, so relevant chunks are less likely to be probed. Your assistant starts returning architecture overviews instead of the fix.
That is brutal, because it looks smart while wasting the engineer's time.
Exactly. Fast wrong answers are strategic debt. In RAG, retrieval quality sets the ceiling. If FAISS training damages recall, every downstream prompt, re-ranker, and model is playing catch-up.
So, what should builders actually do without turning this into a giant clustering project?
Keep it practical. First, know whether your index needs training at all. If you are on FLAT or HNSW, this specific issue is smaller. If you are on IVF, PQ, OPQ, or hybrids, training is mandatory and worth attention. Second, train on a representative sample of your final embeddings, not a convenient sample. Third, retrain when your corpus shifts meaningfully, like new content types, new chunk sizes, or a new embedding model.
And validation?
Measure recall on a held-out set of real queries with known relevant chunks. Compare approximate search against a stronger baseline, like FLAT, on a smaller slice. If recall drops in the exact domains you care about, the training sample or index settings are suspect before you touch prompts.
So the hidden question is not just which FAISS index is fastest, it's what did that index learn from, and who gets sacrificed when it learns the wrong shape.
Yes, FAISS training is where retrieval systems quietly choose their blind spots. Treat that step as product logic, not plumbing.
Because in RAG, the model can only reason over what retrieval found.
And if your FAISS training is off, your system does not just search faster, it forgets faster.